Good morning, class. We will be discussing hydrologic losses for your midterms. Mainly, we will be discussing evapotranspiration and infiltration. We will be understanding the missing water in watersheds. Okay, so first, we are going to tackle the overview. Okay, hydrologic losses overview. These are processes that reduce surface runoff by storing or diverting water. So we have the first one, evapotranspiration, water loss to atmosphere by plants and soil. Next, we have your infiltration, water seeping into the ground. Three, interception, rain tapped by leaves or buildings. And four, depression storages, water held in puddles or depressions. But why are we studying this hydrologic process? They are naturally occurring processes in the environment or the atmosphere. Why though? Why do these hydrologic processes matter? So first, we have your. It is important in flood prediction and urban drainage because cities mostly have impervious surfaces. Okay, impervious surfaces meaning they have uh, roads and rooftops. These roads uh, contribute to the loss of 50% to 90% of natural infiltration capacity, meaning they hinder the rainfall or the water from infiltrating the soil or the ground. Okay? They are being intercepted by these impervious layers. Okay? The water can be stored in rooftops, and the water can not penetrate the soil with roads and pavements on it. Okay, so we have a very not so very recent incident, but you can watch the video, the Houston urban flooding and infiltration loss. Okay, this is a great example of cities with impervious surfaces and rooftops. Okay. And we have here an engineered solution for that specific problem. We have green infrastructure. Even if we say that the roads for this green infrastructure is permeable, the structural integrity of the road is not compromised. Okay, so they designed a permeable pavement, and some they designed permeable roads for infiltration. Okay, and we also have your rain gardens. Then next we have your water supply and drought planning. Okay, so ET or your evapotranspiration, this is its role. Okay, in arid regions, we have 60% of rainfall may be lost due to uh, evapotranspiration. Okay, so why water supply and drought planning? Okay, so the 60% loss of rainfall by the cause of evapotranspiration would be the possible addition to the water supply of that specific region. But since it was lost due to evapotranspiration, okay, so the loss in water supply, meaning the increase of effects of drought in that area. Okay? Its role is to cool down that area. So I cool down and add to the water supply in the area. But since rainfall is lost due to ET, that 60%, that means there is an increase of 60% in the effects of drought and the decrease of 60% to the water supply of that region. So ET is a very important, yet it is one of the most problematic hydrologic causes in this topic. So that's why they invented these smart irrigation systems. For more information about these smart irrigation systems, you can click the link I provided, okay, for you to have an example or visual presentation of the smart irrigation systems. Okay, so third, we have your infrastructure design standards. Okay, so these hydrologic losses matter because they obviously from our first and second exam, I'm first and second topics, they impact design of infrastructures. Okay, there are now specific codes that are followed in some parts of the US in designing infrastructures. They are to account for hydrologic losses. Okay, so there is an example there. You can click it. Then we have your last climate change adaptation. Okay, so we have the warming trend. 1 degree Celsius rise can increase ET by 5 to 10%, reducing water availability. As said before, ET can impact the water supply of a region. Okay, so we have an engineered response, updated IDF curve using future climate projections. Okay, so IDF means intensity, duration, frequency. Okay, an example is in here. I will not be discussing it any further. Okay, you can just click that link. Okay, so let us move on to our part one or the first topic in our midterms. Evapotranspiration, the invisible water loss. Okay, so EP, meaning evaporation plus transpiration. Okay, so the evaporation part is the water or the vapor from soil or surface water, and we have your transpiration. This is the plants sweating through leaves. Okay, so as said from prelims, we have the key drivers of evapotranspiration here. Okay, so we have your solar radiation, yeah, the sun, and the climate. We have your temperature, humidity, wind speed, and we also have your vegetation, crop type or leaf area. Okay, I'm so sorry. Okay, so you now know you knew about solar radiation from our previous topics. Now we have your temperature which was discussed a while ago for the due temperature, the temperature for your ES or the saturated vapor pressure. Uh, we also have your humidity from the last topic. And now we have your wind speed. Wind speed will be discussed further along the slides. And now let's move on to this vegetation or the crop type or leaf area. In evapotranspiration or specifically transpiration, the crop type has a coefficient for its transpiration or the evapotranspiration coefficient of a specific crop type. There are not all plants have the same coefficient and not all plants have the same leaf area. So in our computation for evapotranspiration will be involving the crop type, not specifically um, on the leaf areas, but the crop type or the coefficient for the crop types. Okay, so let us move on to why engineers care about transpiration. Okay, so these are the engineering applications of evapotranspiration. First, we have your irrigation design and water conservation. If you have clicked link from the previous slide, okay, you will be able to visualize smart irrigation. Okay, so the problem is the over irrigation, wastewater, and under irrigation reduces crop yields. Okay, so the solution is the ET-based irrigation scheduling. Okay, this is a video of irrigation scheduling, but as I've said a while ago, okay, so we have the crop coefficient here as part of the formula for our irrigation scheduling. So ETO, or your uh, this is co- this is referred to as water needed for irrigation in some books. Okay, so your ETO is equal to your ET of your crop multiplied by the crop coefficient. Okay, so example, we have this. How much irrigation is needed to sustain a cornfield with an estimated evapotranspiration of 5 mm per day and a crop coefficient of 1.2? Okay, the answer is 6 mm per day of irrigation because the formula is just the ET crop, meaning your 5 mm per day, and the crop coefficient, which is your 1.2. Okay, so 5 times 1.2, we have your 6 mm per day of irrigation. Okay, now we have this a tech tool for that problem. Okay, we have the tech tool, smart irrigation controllers. An example of this is a wheat flow, the wheat flow. Okay, for more information on the wheat flow, you can click that link. Uh, it's up to you if you want to have a uh, visual representation of the wheat flow and irrigation scheduling. I provided the link. Okay. Okay, next we have this reservoir and water supply management. Okay, so ET accounts from the previous slide, 60% of water loss in reservoirs in arid regions. And now we have a new engineering response, or the engineered solution for this. We have your floating solar panels to reduce evaporation, and ET forecasting to optimize water releases. Okay, so from the previous slide, okay, let me go back to the previous slide. We have your irrigation scheduling, but this is not just irrigation scheduling because this is a some sort of ET, if used properly, this can be used in ET forecasting because you already know the crop coefficient and you already know the estimated evapotranspiration of the specific crop. You can use this to uh, forecast the upcoming evapotranspiration. Okay, so let's move on to the floating solar panels to reduce evaporation. There is an example here, but I will just tell you. Okay, the floating solar panels that in hydrologic matters. Okay, these floating solar panels reduce the evaporation. Why? Because they are on the surface of the water, covering the surface of the water. Okay, while in covering the surface of the water, there is still um, evaporation, but very minimal because the heat, or the key driver of evaporation, um, the heat from the sun does not uh, come in contact more directly with the water because we have your solar panel on top of the water surface. Okay, that's just the overview of the floating solar panels floating the effect of floating solar panels on evaporation in a hydrologic sense matters, but in energy and in some other concepts, you can click the link to see a very short video of floating solar panels. Next is we have this uh, urban heat island mitigation. Okay, so the science behind this is plant cool cities via transpiration. Okay, we have a design application of this. Green roofs reduce building temperatures by 5 to 20 degrees Celsius, and one mature tree is equivalent cooling to 10 AC units. Okay, energy wise, this is very good. Um, this can also help in climate change, okay, global warming. Okay, so let me explain these green roofs for this moment. Okay, green roofs are as I said a while ago, rooftops intercept water, but not in your green roofs. Okay, these green roofs are rooftops, yes, but they have vegetation. Okay, they have plants on their roofs. Okay, so in added insulation from the heat, we have soil, and we also have the plants that are planted on the soil on the rooftop of the buildings. Okay, so insulation wise, they can reduce the temperature of the building. Okay, and uh, they can also help with the natural process like infiltration and transpiration. Okay, because of the plants that are planted on the roof or rooftop. Okay, and we also have this one. The one mature tree is equivalent to cooling of 10 AC units. There are some buildings I did not have time to look for. There are some buildings that have trees inside of the building. Okay, so this helps reduce the temperature and reduce the use of AC units in the buildings. Okay, so that is one way of using the concept of evapotranspiration for cooling or mainly the transpiration. Then we have last one. We have your why engineers care about evapotranspiration. We have climate change adaptation. Okay, so according to the data, we have 1 degree temperature rise to 5 to 10% heat increase. Okay, so the infrastructure impact, we have longer drought periods and need for larger water storage capacity. Okay, so why? Okay, so yeah, the infrastructures nowadays, even if we have green buildings, we still do not have green building codes. Okay, I cannot seem to find a green building code um, involving the this hydrologic losses or the evapotranspiration. But there are still some who are considering green building as a answer to climate change. The buildings nowadays do not consider the effect of hydrologic losses in their design. Okay? So buildings have high temperature not the buildings not the green buildings, but the usual buildings have high temperature and high energy usage, which can bring high temperature, global warming, and other impacts. So there is a great need for larger water storage capacity because water is one of the main cooling agents of cooling systems. Okay? Water is the one of the main agents of cooling systems. So they're going to need bigger water storage capacity. And with the rainfall loss due to evapotranspiration, as mentioned before, there is a high tendency or the high possibility of increasing water supply storage if you do not know how to uh, forecast your evapotranspiration, or you do not know how to schedule your irrigation. Okay, so a video link is also there if you want to uh, see the infrastructure impact of climate change. Okay, so now we move on to our estimation methods. There are methods of estimating evaporation and transpiration. Okay, so this will be our um, last topic for today. We will be having more topics of this for midterms. Okay, first estimation method of evaporation. Okay, so we have your mass transfer approach. Okay, the origin concept of this mass transfer approach is it was developed based on the Dalton's law of 1802, which states that evaporation is driven by the difference between the saturation vapor pressure, or what we call your E of S, at the water surface and the actual vapor pressure of air above it. Okay, the idea is that the evaporation increases with wind speed and vapor pressure gradient. Okay, we have a formula, the main formula. E is equal to CE multiplied by the quantity E of S minus E of A, where E is your evaporation in mm per day or in cm per day. CE is the empirical evaporation coefficient. Okay. ES, the saturation vapor pressure at water surface, usually in pascals or mmHg, the height of mercury in your, I think that's the barometer. E of A is equal to actual vapor pressure of air, uh, also in PA or mmgh. And we have here refinement that includes wind function modifications because it is stated above the idea is the evaporation increases with wind speed. Okay, so refinement include wind function modifications leading to formulas like this one, the original formula multiplied by 1 plus bu, where u is the wind speed and b is a coefficient. Okay, so to further understand this mass transfer approach, we have ah we have the limitations. Sorry, I thought we have the example for the next slide. Okay. So first we have the limitations for mass transfer approach. This assumes evaporation occurs only due to vapor pressure differences. Okay, so if we add or if we consider the solar radiation, we cannot use the mass transfer approach. Next, we have it needs site-specific calibration for CE. So this means that if you are going to a place where the coefficient of evaporation has not been estimated or has not been computed, you are going to compute for the CE on that specific site, okay? And not reliable over land surfaces with vegetation. Why? Because we are just computing for evaporation, not transpiration. We are not computing for ET. We are just computing for the E in ET, which is your evaporation. We have the applications. Of course, we have your large water bodies because in the limitations in limitation number three, this is not reliable over land surfaces, meaning we will be computing the evaporation of large water bodies like lakes, reservoirs, and ocean. Number two, we have climate studies, okay? Estimation of evaporation loss in weather models. And we have engineering projects assessing evaporation in hydropower dam. Okay, so now we have your example. Okay, a lake has a surface temperature of 25 degrees Celsius. Air above has a vapor pressure of 1.5 kPa, while the saturation vapor pressure at 25 degrees Celsius is 3.17 kPa. The empirical coefficient CE is equal to 0.00039 kg per m squared s kPa, and the wind speed is 4 meters per second. Estimate the evaporation rate. So first, we identify the given. We have ES or saturated vapor pressure 2.17, actual vapor pressure 1.5, evaporation coefficient given. We have the wind speed as 4 meters per second and the coefficient as zero point 0.5. Okay, so the solution, just substituting the values to our formula or the refined formula. So we have CE 0.00039 multiplied by the quantity of E of S, which is 3.17, minus E of A, 1.5, multiplied by 1 plus B 0 point 0.5 multiplied by U, which is 4, is equal to 0.00195 kg over m squared s. Okay, so there we have here a conversion since 1 kg over m squared s is equal to 86400 mm per day. We can say that E multiplied by that is equal to 168.5 mm per day. Okay, so our final answer, the evaporation rate, is 168.5 mm per day. So that concludes our topic for today. There are still three methods of estimation for evaporation, and we will still be discussing infiltration for the following days or the following weeks before midterms. Okay, so thank you everyone. I hope that you learned something today. Okay, this ends our lesson.